All right, so let's start with the content. So last time we've been talking about torsion, right? Remember, as you see here, if you have a shaft, we call shaft, it's basically a bar. Now it's under axial movement, and we call it torque. So when you have a bar under axial torque, then it will generate a deformation, a twist deformation. So then we base on the observation that the cross sections will remain as a plane, right? And based on that, we derive how much deformation you're going to get. And here is the equation. So the first one, you see the angle of twist of a segment, right? That will equal to the torque times the length, then divided by G and IP. Right? So that has to be a uniform segment. Okay. By uniform, we mean the torque is constant in that segment. The material is constant in the segment. And the shape, the IP, will be constant in this segment. Then you can throw everything out at that integral, and you get this equation. Right? Now, today we're going to deal with one situation. That is, when you have a bar that is not uniform. Okay, you have several uniform segments. Then, how can you get the total rotation angle? All right. And the general idea we already talked about last time. You just divide up into several segments, right? And if for each segment, you calculate how much rotation there will be, and then you add them together. So the idea is the next second equation. It's very simple, right? You add all together, that gives you the total. Okay. But when you do it, there are a few things easy to make mistakes. So therefore, we're going to go over a couple of examples together today as non-uniform bars. How can we get the rotation angle? All right. So let's start with this one. Let's show here. Okay. So you have this bar here. This shaft here, right? And the two torques. One is T1 applying at point B. Another one, T2 applying at point C. So how can we find out the rotation angle of each segment and then get the total? Okay, so first, how many uniform segments do you have here? You have two, right? Some will say, oh, there's a transition point there at point B. You see there? That's a tiny, tiny portion. Remember what we said before. We ignore that part, right? So transition point, we always ignore it. So therefore, we have two uniform segments, right? So for this reason, what we need in finding out the torque will be looking at, for each segment, how much rotation it will have. Okay, let me get the pen into insert. Hold on 1 second. Okay, just read. Okay, so give me 1 second. I just need to pull this down a little bit. Okay, here is insert. Okay, so we need to find out the torque in this segment, right? And also the torque in the other one. Also the torque in this segment. Okay, so how can we find out the torque in this segment? Oftentimes we like to use T1, T2, right? Segment 1, segment 2. But here, T1, T2 already using, right? You see here, T1, T2, that's the external load. So we cannot use T1, T2 because it's confusing. So we need something else. Okay, what do you want to call it? How about the T AB, and then this one we call it TBC. Right? Just distinguish from the load. Okay. So how can we find out the TAB and the TBC? How do you find the internal force or internal movement in this case? Make a cut, right? Free body diagram. And then you find it. Okay, so we make a cut here and make a cut here. Okay, let's say if I cut it here, right? So I'll just draw this segment here. All right, so here I have T, this will be T2. Okay, now here's a reaction. I call TBC, right? Okay, why do you draw the arrow leftward? I don't know which way, but I always assume it's a positive way. It's easier. I don't have to make a judgment. I just say, oh, here is positive. Let's calculate the value. If it's negative, then you know it's different direction. Okay, so positive again is when you have a shaft, this is the cross section. If it's pointing away from the surface, that's positive. Right, right-hand row. So that's positive. All right. So that's the free body diagram. Okay, now for this part, if I cut this one here, there are multiple ways I can draw it. Right? So I can draw, for example, I can draw the right side. So that's what I have like this. That's the right side of this cut, right? So, or I can draw actually this one. Right? I can draw between the two cuts. That's all options. I can just select this segment or select the bottom one. Okay, either one will be fine. Right? And then later on you will get a sense gradually after you do a few problems. You get a sense which one you prefer. Right? It's all okay. Okay, let's do actually for this time just do both. So if I draw this whole thing on the right, then I'm going to have T2 here. Right? T1 is here. Okay. And then I'm going to have the TAB here. That's what I'm looking for. Right? Okay. If I draw the bottom one, then on this side, I'm going to have what's here? TBC. Right? Okay, what's here? TAB. Right? The same, TAB. Okay. Now, is this complete? Yeah, this free body diagram complete. Yes, there should be a load. You forgot to label the load, right? Oh, I forgot to label the load. Right. Okay, so here is the other one. That's the T. Oh, I needed that picture to show which direction. Going upward. Okay, so there will be a T1 here. So this will be T1. All right. Okay, so that's the free body diagram. Now, equation of equilibrium. All right. For the top one, the very first one, this one, what's the equation of equilibrium? You're going to have negative T BC, right? Then, for this very first one, plus T2 equals 0. Okay, now what's TBC? Equals T2, right? Okay, so if you know T2, actually we know, right? T1, T2 are the load. You can give a value. One is say 10, one is 5, or one is 10, one is 5, one is 8. You can give any value you want, right? But we can find out TBC here from here. So this will give us TBC equals T2. Okay, now for the bottom two, let's write the equation of equilibrium. Okay, for this one, what's the equation of equilibrium? You're going to have negative TAB, right? Then plus okay, T1 and T2, there are different directions, right? Okay, so for T1, it's a plus or minus? It's a minus. Okay, so it's a minus T1, right? Okay, what about T2? It's a plus. Okay, T2. So this will equal to 0. Now from this one, can you find out TAB? From this equation, can you find out TAB? Yes, right? Okay, you have a question?
Yes, why is TAB, why are you writing it negative if you say that it's outward, it's positive?
Okay, all right. So what's positive, what's negative? Again, when we say positive or negative in this class, we talk about deformation. Is a positive deformation or negative deformation? So if you apply a torque here, right? And then on this side, you have to have two right hand. Okay, I just have one. So this one here. So this one here, that's a positive. Okay, this one this way, and then this one this way. That's a pair. Generate a positive deformation, we call it. So this kind of deformation is a positive deformation. All right? So therefore, these two are a positive pair. That's for deformation. That's what we use here. However, now recall what you learned in statics. If you have a moment this way, one moment this way, how do you write the equation of equilibrium? How do you write the equation of equilibrium? You need whatever direction you call positive, right? That will be negative, one will be positive. So that's the difference between when you talk about deformation, what's positive, and when you talk about equation of equilibrium, what's a positive. Okay, so here we always have a positive pair. In statics, we never talk about positive pair. Because here you have to have a pair to generate deformation. Otherwise, if you just apply one, there won't be deformation. It will be just rotating, spinning up, right? Acceleration. All right? Yes?
So T2 is equal to T1 and TAB.
T2 is equals to, yeah, that's right. Yes, so this equation you can derive anyway, right? So the one will be equal to the other two combined. All right? Okay, now what about this one? If we use this very last free body diagram, what's the equation? So you're going to have minus TAB, right? Then minus T1, and then plus TBC equals 0. Right?
Sorry, how did you get the plus T2 and minus T2, like the sign?
What?
Did you say clockwise and anti-clockwise, or?
When you write the equation of equilibrium, you define, okay, this way positive, then whoever this direction is positive, whoever against this direction will be negative. That's when you write the equation of equilibrium. So in the second equation, for example, TAB, you have this way. Now T1 is this way. So it's the same. They're both negative. And then T2 is this way, so it's positive. Always right hand, right? Sometimes you draw a double arrow. You use the thumb, say, oh, this is positive. Sometimes you use your fingers, so you just draw the curved arrow. So that's also positive. This one, this 4, they mean the same thing. Right? Yeah. Okay. So curved arrow or this double arrow, they mean the same thing. Right? It's just one of your hand, right hand. Okay. All right. Now, if you look at the last equation, okay, can we find out TAB and TBC from the last equation? Not by itself, right? But actually, if you look at the last equation, is the last equation independent? Can you get the last equation from the first two combined? Yes. That's why your independent equations is limited. You can cut many free body and draw it and write the equation of equilibrium as many as you can. This one, for example, you can draw maybe 5 different or 6 different combinations. But the independent equations, there are only 2 of them. One is for this part, one is for the other part. Right? But fortunately, you don't have that many unknowns. You just have 2 unknowns, and you can always get 2 independent equations. Right? So my point is here, I wrote down 3 equations, but they're not independent. There are only 2 independent ones. The third one you can get from the first 2. All right. Okay, so in a sense of, is this problem determinate or indeterminate? It's determinate because based on equation of equilibrium, I can find all the internal force reactions, right? For example, if I want to find out what's here, the reaction, TR here, can you find out the TR? Can you find out the TR, the reaction moment on the wall? Yes. You can write the equation of equilibrium for the whole thing, right? Or you can just write the equation of equilibrium for this part. So you can find it, because we already know TAB now. Right? So this is a determinant problem. And that's why it's easier to start with. Okay, anyway, now back to this problem here. Right? So from here, what we show here, you find out the TAB and the TBC. Okay, so we know TAB and the TBC. Now, can we find out phi AB and phi BC? The AB segment, how much it rotates? Can we find out? Yes, because I already know TAB, right? So the equation will be TAB here times L1, and then G1, IP1, the segment 1, right? And then the second one will be TBC, and then L2. Or you can say LBC, and then GBC, and then IPBC. And what's the total? You will find out phi equals to phi AB plus phi BC, right? All right, so we're done. So this example actually can be many examples here, because we didn't give any value there. Just generally, we kind of find out the relation. And you see the steps. You cut the free body diagram, figure out the internal torque of each segment, and then you use a rotation angle equation, right? Use this equation, and then you get the total. So that's a kind of general step. So this can be as many examples as you want. All right. So next, let's give some numbers. Okay. So we can see how things can be different in different situations. Okay, let's say if I have T1 equals to, let's say 20, T2 equals 5. Okay, so I'll just make it easier. So I just draw it here. Okay, so T1 here also will be 20. This is T1. And then T2 here is 5. Now my question will be TAB. What's TAB? What's TBC? How do you find out TAB and TBC? You make a cut, right? What we just did. So you make a cut here, make a cut here. All right, so that's what we have here. So for first one, so you know this one equals 5. So what's TBC? Equals 5. Right? Positive 5. That means this part get a positive rotation, 5. Okay, so let's write it down here. So TAB equals 5. Now what about TBC? Oh, so we got the opposite, right? TBC equals 5. Okay, so TBC equals 5. All right. So what's TAB then? Okay. If you don't want to think about it, you just follow the equation. So from here, you get the TAB equals T1, right? T2 minus T1. Okay, T2 minus T1, that is 15, right? Now, why is 15? Okay, if I cut here, so on this side, so you have T2 here. T2 equals 5. So I say, oh, this part will equals 5 as well. Now, what about this one? If I cut here, okay, so here I have T2 equals 5. You see, sometimes I just either use a curved arrow or I just use double arrow, depending on which one I like, right? Okay, so here is T1 equals to 20. Okay, so here is TAB. Okay, why TAB equals 15? Positive 15 or negative 15? Okay, so think here. T2 5. So you twist this way 5. And then this one twists this way 20. Therefore, to balance, TAB must be which way? Follow T1 direction, right? How much? 15, right? Because this way, 15 plus 5 at the end, 20. Then in the middle, you have 20 this way. So they will balance. So therefore, TAB should equal to what? Negative 15. So it's not positive 15. Right? Okay. This one, it's very similar to last chapter. When you have two forces applying there, if you have N1, P1 equals 20, one way, right? This way. Now you have a P2, 5 that way. So what's the reaction force N here? NAB will be negative 15. Right? You know what I'm talking about? So let's draw it here. Okay, we try to review chapter 2 because the exam is going to come up. Okay, so if I have a force P2 here equals 5, I have another P1 here, P1 equals 20. Okay, now what's the N here? N will be negative 15. That's what we just did, the quiz, right? So the quiz is the same thing here if you have a torque, right? So I can give you a same quiz, just change all the forces into moment, into torques, and then you should still be able to find out, and then that means you understand. All right. Okay, so back to this one. So we're going to have TAB going to be negative 15. All right. Now, when you calculate the total angle, what happens? These are for I'll review previous one, right? So I can throw it out. Okay, so when you calculate the total angle, how do you calculate? What's the total angle? So you're going to have, see here, what's the equation? Right? You add them together. Now, how you add them together? In this case, in the red ink situation. TAB, right? So here you should have negative 15. 9 times L1, G1, IP1, right? And then the other one plus TBC. So that's 5. So L2, G, IP2. Right? So what does this mean? That means the middle part going to maybe depend on the stiffness or rotate a negative angle. But the BC segment going to rotate positive angle. So the total angle will be, the value actually will be smaller. They will cancel each other a little bit, right? One goes negative direction, one goes the positive direction. So the total is actually minus each other in terms of the values, absolute values. Right? Yeah.
T1 and T2 are both positive, even though the current is in different directions.
No, they're not both positive. One is in terms of equation of equilibrium. Okay, one is positive, one is negative.
But you said T1 equals 20, T2 equals 5.
Yeah. Yeah, I'm saying T2. Okay, T2 is 5 going this way. There's no negative or positive thing here. This is just a load. I'm saying the load going right, 5. The load go left, 15 or 20. So this is just a load. Load, I'm telling you this direction. So I say this direction 5, this direction 20. Right? So here is no positive or negative issue there. It's just a load.
I think I gotta see what you say. Like if you just said T1 equals negative 20, that would be correct. But if you're labeling that arrow, you're just labeling a magnitude on that arrow. You
Yeah.
can figure out the negative positive.
Yeah, so in terms of load, there is no positive negative. You know, like a force, I'm saying, okay, force, you're applying force here, 5. Or you're applying force here, 5. I'm just saying which direction you're applying force at the amplitude of 5. In terms of positive, negative, that is when you look at the internal torque here, it's a positive or negative. That means you generate positive deformation or negative deformation, right? Okay, so that's different thing. One is the load, one is your internal force or internal movement. We talk about sign convention for the internal force and internal movement. We're not talking about the sign convention for load. Load can be any direction, right? You just label there whichever direction they give you. All right. Okay, any other questions? No? All right. Okay, so now if no question, let's do another practice. Okay, so if I have a bar here, I'll make it a little bit easier so it's uniform. Okay, so now I apply two loads. One is a torque here. Okay, let's don't use T1, T2 anymore because somehow people get confused. So I can say this will be the T end. Okay, at the end there is a torque equals to 15. All right, and then in the middle here, I have a load. I call it T middle. Right, this one just applying in the middle equals to let's say 5. Okay. Now I want to find out. I know all the geometric material information, right? So GIP is known. Now I want to find out what's the total rotation angle here, phi. And I also want to know what's the torque in this part. What's the torque in this part? Basically, you have two segments, right? This one, although geometrically it's uniform bar, but because you have a load here in the middle, so it becomes non-uniform bar. Because the two segments, the internal torque going to be different. All right. So what I need, it will be T1 here, T2 here. What's the value? And then calculate the total angle. We know it will be phi 1 plus phi 2. Right? Okay, so what's T1? How do you get T1? Free body diagram. So you make a cut here, and then I can draw this right part. Right? So here's the T1. All right. Now the load, I need to label the load. So you're going to have a Tm here, and then you're going to have a T end here. T end here, right? Okay. Equation of equilibrium. What's the equation of equilibrium for this one? So negative T1 plus Tm plus T end, that equals 0. So what's T1 from here? 20. Okay, why is 20 now? It's like, okay, I'm holding this bar, right? Someone here is twisting 15. Someone here is twisting 5. So how much load moment I have to apply here to hold it? Because all of you move in the same direction. So therefore, I have to apply load here, balance both of you. So therefore, it adds up together, right? Now, if we have this situation, okay, what's T1 actually? What's the T2 here? We haven't finished this part. What's T2 here? T2 equals to, okay, so this will be 5 plus 15. So it's 20, right? So this will be equal to the end, so it equals to 15. All right? So we got this problem done. Now I want to change the problem a little bit. So we have this situation. Again, I use the red one. So if I have this same bar here, okay, so this part is still 15. T end equals 15. But this part, the load, someone applying load this way. So the Tm equals 5 this way. Okay, now what's the T1 here? What's the T2 here? What's T2? 15, because you have this free body diagram here. same, right? Okay, now what's T1? Okay, wow, you guys quick. Okay, so let me draw the free body diagram here. So you're going to have T1 here, and then you're going to have Tm here. Tm, that's 5, right? And then this will be, now again, this is a load. There's no positive, negative. Right? Just say, oh, the load is loading this way. So load, there's no positive and negative issue there. It's just whatever they give you, which direction. When you write the equation of equilibrium, okay, if you follow your line, it's positive. If it's against, then it's negative. Right? Okay, now for this one, what's the equation of equilibrium? For this one. So you're going to have negative T1, negative Tm, then plus Te equals 0. So therefore, your T1 equals positive 10. Okay. Now, why this one just 10? It's like you have two guys applying load here. One is pulling this way, 15. But the other guy is going this way, 5. Right? So you have one guy very strong, twists this way. But another weak, a little bit weak guy twists this way. So what I feel? I feel only 10 because one is turning this way, the other turns the other way. So you two actually cancel out some. So from me, look at the outside, from far away, what I feel, it will be just 10. Right? Because you two cancel a little bit. So physically, that's how you understand it. Mathematically, it's just easy. You just follow the equation, right? All right. So therefore, you need to set up this kind of things. Okay. When the two are twisting the same direction, they will add together. So to this end, will feel more. But if the two somehow opposite direction, then the end will feel less because you two cancel each other a little bit, right? And then you just end up there. Okay. It's the same, like if you are pulling tug of war, right? So if everyone pulling here, then the total force will be everyone's pulling force add together. That's why you have a strong team all pulling here this way. But if somehow if one guy is not the same hard as the same team, just pulling this way, then if you have 10 of you, then you actually only 8 of you. Because one guy pulling this way will cancel another person. So you will be only 8 of them. So that's why you don't want a guy in your team somehow not with you, right? Just pulling the other way. So basically the load can be add together or cancel out some, depending on the direction. Yeah.
Just make sure I'm with you here. If you were to ask for the reactionary torque at the end, it would be T1.
So this here, the TR, okay, is basically equal to T1. Because if you draw this part of free body, this is the two sides of the load. So it will be supposed to be equal. Yes. All right. Okay. Other questions? All right. Now, is a non-uniform bar easy or challenging or okay? Should be okay, right? Just calculate one, uniform, then calculate the other one. The only thing you need to pay attention is, okay, judge how many segments do you have? That's depend on how many parts that's not uniform. That's one. So when you calculate the internal torque, just careful, draw the free body diagram, write the equation, find it out. Okay. What's the common mistake come from? Oh, just look at this one. So I just look at this very top here. So I say, oh, here and here. Just somehow jump, give the number. Okay. Another fundamental thing, again, is you never cut here. Because you don't know this 5 is shared how much by the left side, how much by the right side. You can never divide it because you don't know how it deforms yet. Right? So never cut at the transition point. You cut anywhere in the middle, it will be fine. And then you have the free body. All right. Okay, so we're going to have a few homework problems. You can examine this as practice. All right.
Just don't use your free body diagram here now. Use your uniform.
Yeah, never cut in the transition point. That's the rule. Okay. Never cut in the transition point. So like this one, you never cut at point B. You know, any point you can cut except point B. All right. Anywhere you can cut, it will be fine. But don't cut at the neighborhood of a point B. Because you can never say the T1 in the middle is belong to which one, how much is on this side, how much on this side. Because actually, when you have a bar, you're applying a load here. So this load will be shared by this side and this side. The problem is you don't know how much share this side, how much share on this side. Right? So you never cut at the middle. Right? Yeah.
Same thing when I'm doing my compressor, it tends to.
Yes. So never cut in the transition point with a dividing point. Yeah, for non-uniform bars. Or for indeterminate bars. For anything, never cut it there. All right? Okay, any other questions? All right, if not, let me end by look at this one problem here. Okay, so now let's say I have this bar here. I fix this bar to both sides, both ends to the wall. Okay, this shaft, applying a moment here. Let's say I don't apply in the middle. I apply 1/3 of it. Here is a TEM equals 5. Applying the 1/3 of the location. I mean 1/3 of the length from one side and 2/3 of the length from another side. Okay, so now the question is, what's the reaction here? So you're going to have a TR at point B, right? Actually, this one is point C. I think this will be point C. So this point B here, and this point A here. So what's the reaction here? TR at point A. Yeah.
Can we, just sort of like the other one that we can determine intuitively, or we can say the reaction of TR is going to be 1/3 of TM, and then the reaction.
How do you know it's 1/3 of the TM?
I don't know. But
You don't know.
the length of motion.
So you have to set up the equation. You find out, right? After a while, you do a lot, then you can say, oh, is this 1/3? Actually, I can tell you, your answer is wrong. It's not 1/3. It's 2/3, actually. It's 2/3 is here, actually. All right. But anyway, how can you know about the value? You have to set up the equation, find out the values, right? Okay. So let's set up the equation. Okay. What if you cut here? You can cut here, right? Or cut here. So if you cut here, you're going to have a T1 this segment. You're going to have a T2 in this segment. All right. So if I cut here, let's say I cut here. So this is the segment I'm looking at. All right. So I'm going to have a T2 here. I'm going to have a T1 here. All right. So the load is applying here. That's the TM. All right, now what's the equation of equilibrium? For this free body diagram. So you have TM positive, T2 positive direction, and then minus T1 in the negative direction equals 0. All right? I cannot find the T1, T2 because there are two unknowns. One equation. Oh, how about I write this one, top of the one? So I'm going to have a TM plus, well, there's no plus. I assume it's the other way. The load is the other way, right? So it'll be negative TR at C, negative TR at A equals 0. Right? Because somehow I assume it going that way. I guess because I got the sense, oh, you're trying to twist this way, therefore I have to hold it the other way. Right? Just guessing. Right? Okay, so it will be this equation. Now, can I find out TRC, TRA? No, I cannot, because two unknowns, one equation. Okay, what's this situation? Indeterminate, right? So now we have same situation, indeterminate shaft. Okay, once you realize now it's indeterminate, okay, how do you solve it? The Fed.com, right? So the same trick. Okay, so let's see how can we use the Fed.com to solve this one. Free body diagram, so I just draw it here, right? And then equation of equilibrium, I just did. So I already did the two steps, right? So the F, E, already did. Then I need the deformation equation. Okay, what kind of deformation you have in a shaft? Rotation angle, right? Twist angle. Okay, so what I have will be, okay, so the D means phi 1 equals to T1, L1, G1, IP1, right? And then the second bar, phi 2, will be T2, L2, G2, IP2, right? Okay, so the Fed part is complete. Now, what's the com part? Compatibility. What's compatibility? The relation between the deformation parts, right? Which part deform? How this deformation, they match each other. They agree to each other. They compatible to each other. Okay, now, what's phi 1 here? It's a rotation angle of this segment, right? What's phi 2 here? It's a rotation angle of this segment, right? It's the AB segment rotation. And the BC segment rotation. Okay, so how are they related? Okay, let's say if the AB segment rotates 1 degree positively, then the BC segment must rotate negatively 1 degree. Why? Because if you look at the end, it moves 0, right? From this end to the other far end, it moves total of rotation angle of 0. So we have a compatibility now. So the compatibility will be phi 1 plus phi 2 equals 0. Or someone may say, oh, I want to say phi 1 equal to phi 2. Is that correct? Yes. Yes, value, right? I'm put the absolute value there. So the rotation angle, in terms of value, one goes this way 1 degree, one goes the other way 1 degree. Their value equal. Right? Okay, which one better? This one I think is better, right? When you put the absolute there, it's hard to solve the equation actually. Right? Or sometimes I say, oh, phi 1 equals negative phi 2. Right? You have to rotate the other direction. I rotate 1 degree here, you have to rotate the other direction in the same angle. So that's why phi 1 equals negative phi 2. But fundamentally, all three equations, they mean the same thing. All right. Okay, now, can we solve it? Yes, we combine all the equations. All right, so we can pick one. You can use, let's say, use this one. Okay, so take these two equations into this one. Now it's a mathematical equation, solving problem, right? So you have the equation 1, you have equation set 2, and equation set 3. So 3 set of equations. You combine them and solve it. Actually, we have 4 equations here, right? All right, so solve it. So I will do it this way. So because phi 1 plus phi 2, this is the solution part, all right, equals 0. So I have T1, L1, GIP plus the T2, L2, GIP equals 0. Is that true? Yes, okay. GIP cancel out. Okay, L1, L2, what's their relation? It's a T1 times 2. right? 2/3 of the length, or 2a, plus t2, 1/3 of the length, equals 0. A. Right? So what I got will be t1 plus t2 equals 0. Okay, now what else I got? See here, this part. So let's copy that. So I have Tm, that's Tm, then plus T2 minus T1 equals 0. In other words, I have T2 minus T1, actually T1 minus T2 equals Tm. And that's known, right? So this will be equation 4, equation 5. If I combine this 4 and 5, can I find the T1, T2? Can I find T1, T2 from these two equations? Yes. Okay, immediately I can find T1. Okay, add these two equations together. What do you get? Add the 4 and 5. What do you get? 3T1 equals Tm. So therefore, Tm equals 1/3 of T. Oh, T1 equals 1/3 of Tm. That is, on the left side, okay. So if you look at this figure here, on the left side, you can have, I'm looking at this picture here. Okay, on left side, T1 is 1/3 of Tm. So how much is T2? 2/3. That's why I said you were wrong.
Actually, we got our orientation wrong. I was talking about T1.
Yeah, so T1 is this direction. Yeah. T1 on this side is 1/3. T2 is 2/3. Yeah. Okay. So why is T1 1/3, T2 2/3? Physically, how you explain? Because you are rotating the same angle. Now this part, shorter segment, you want to rotate the angle, so you have to apply a bigger load. This part, longer, you are applying the same 1 degree. So your load here will be smaller. All right? Yeah.
Conceptual, I just noticed that 5-1 plus 5-2 equals 0, which means our total line is 0. That's because we have two big skins, and so they get more.
Yeah. Yeah. All right.